All right. Well, thank you very much for the invitation to be here. It's an honor to participate in the celebration of Jim Arthur's work. His work has influenced my work profoundly over many years, both learning the beautiful theory of automorphic forms from his paper and also motivating many of the things I've worked on. And this is certainly the case with what I'm going to talk about today, which is very much centered around this work, his book on the endoscopic classification of automorphic representations of classical group, which itself was a culmination of decade-long work by him and also by other people on the development of the trace formula, the theory of endoscopy. So I want to begin by discussing the results from Arthur's book that was published in 2013, which WeTech did some of that too, so there will be a little bit of overlap. So let me begin very briefly with a motivation of what these results are about. So F is a number field, and A is the ring of Adels, and G is going to be, for a moment, a general connected reductive F group. And the main object of study in the theory of automorphic forms is the Hilbert space of square integrable functions on this quotient, the adelic points of G modulo the rational points of G, which has already in multiple talks been abbreviated as brackets G. And the objects here have rich arithmetic, and studying them gives a window into deep number theoretic properties. And what we'd like to understand is the decomposition of this space under the action of G of A into irreducibles. And it is well known that this space doesn't decompose discretely into irreducibles. It decomposes roughly into two large summands, namely the part that decomposes discretely into irreducible. So this decomposes as a direct sum, Hilbert direct sum over irreducible representations with some multiplicities. And then a second part, kind of a complement, the continuous spectrum, which decomposes into purely continuous direct integrals. And even though this sounds conceptually much more complicated, actually it is much better understood by Langlands' theory of Eisenstein series. So this can be understood as a direct sum over Levy subgroups. And because I've already isolated the discrete spectrum here, these are going to be proper Levy subgroups of the parabolic induction of their discrete spectrum. And then I'll have to take, I don't have much room here, but I should have to take invariance under the relative Weil group. And so really the mystery is to understand the discrete spectrum, which is conceptually easier because we're just talking about which representations of the adelic group occur and to what multiplicity. And once we understand this, we understand the general case. So this is what the Arthur-Langlands conjectures are about. So I want to describe Arthur's results from his 2013 book on the endoscopic classification of representations. So here, G is going to be quasi-split classical group. But in fact, for a simplicity of exposition, I'm actually going to consider either the split symplectic group or the split odd orthogonal group that WeTech also mentioned in his talk. And so then we have the following theorem due to Arthur that has multiple parts, both local and global, that interact with each other. The first part is the decomposition of the discrete spectrum of G into pieces according to discrete Arthur parameters. This is very much what we saw in WeTech's talk already. Here, what are Arthur parameters? Well, we can define them in quotations to be certain homomorphisms from the Langlands group of F together with a copy of SL2 into the L group of G, taken up to G hat conjugacy. And well, there is some condition, so it has to be continuous and algebraic on SL2C. Let me not write this out. An important condition I will write out is that the restriction to LF is bounded. Okay, and I write this in quotations because the Langlands group of F is conjectural, it's not known. And Wittek already mentioned how one can circumvent this problem and give a non-conditional definition of this using cuspidal automorphic representations of GLN. I don't want to go into that, but in order to remove the quotation marks, this is the thing that one needs to do. But even after one has defined these so-called formal global parameters, one can still define the centralizer group of the parameter, which in the quotation definition is simply the elements of G hat that centralize psi. And in terms of those, one can define the square integrable parameters to be those whose centralizer is finite, at least in this particular setting of the groups that I'm looking at. And so this explains the notation in this first part of the theorem. Of course, this is still, I mean, this is a very useful decomposition, but it's not the only thing we want. We want to understand what is inside of these pieces. And for this, we need local information. So the second part of the theorem is local, and it ostensibly doesn't have to do much with the first part, but afterwards the two will connect. So for any place V of F, we can find all tempered representations of GV. And this GV is going to be a shorthand notation for the FV points of G for me, so the local group. This can be decomposed as a disjoint union over tempered or generic local Arthur parameters of local Arthur packets. This decomposition sits inside a not disjoint union that now runs over all Arthur parameters of packets that may have overlaps. And this in turn sits inside the unitary dual of GV. So this is some subset of the unitary dual that contains the tempered dual. The tempered dual has this nice disjoint union decomposition, and this subset of the unitary dual has this non-disjoint union decomposition. The definition of these local parameter spaces is the same as the definition of the global parameter space, in that these are homomorphisms from the Langlands group of the local field times SL2 to LG up to G hat conjugacy. But now I don't have to put quotation marks anymore because the Langlands group is unconditionally defined. And as Wittek already mentioned, it is just the Weil group if F is Archimedean. And a version of the Weil-Deligne group where we take the Weil group and product with SL2C when F is non-Archimedean. And so now we have two SL2Cs here in the setting of, in the setting of a local non-Archimedean parameter. We have the SL2C that comes from Arthur's formalism. And so I want to decorate this with A. So this is Arthur's SL2. And then we have the SL2 coming from the Langlands group of F. I should decorate the F with a V. Maybe I'll decorate my psi here with a V2. And this, I'm going to give a superscript D for Deligne. So we have a Deligne SL2 and we have an Arthur SL2.
I don't want you to change your slides, but did Deligne always use sort of an affine line?
Deligne preferred, you're correct. So the lean preferred, and I never know with semi-direct products where to put, so I'll put it on both sides. But now, what does better mean? So if you're considering homomorphisms and you have complex coefficients and G-hat conjugacy, then they're equivalent by Jacobson-Morozov theorem. Now, where they stop being equivalent is where you start looking at model coefficients, L-adic coefficients, and then and you look at moduli spaces of such parameters, then actually you get different moduli spaces, and this is better than this. On the other hand, for our point of view, this will be more convenient because there is a certain symmetry of having two SL2s, and that will become crucial. So different point of views.
I would ask the same question about the Arthur.
But maybe that should be directed to Arthur. So let's stick with SL2 for now. There is a third point where now we want to understand. See, we're heading towards understanding the internal structure of this. And the first step is to understand the internal structure of the local packets. So again, for any place V, there is a map from the local packet to the set of irreducible representations of the local centralizer. Maybe we can write it as pi v goes to rho pi v. And so this map has to satisfy certain properties. I'm going to call this property ECR. I'm not going to explain it right now, but maybe in about 10 minutes I'll go into it. So it's not a random map. But let's just finish stating the main theorem, because now we can go back and describe what this is. Namely, again, for any place V, there is a localization map from the space of global parameters to the space of local parameters. Now, if you define global parameters with quotation marks, then the localization map is very simple, because it is expected that the Langlands group of the local field maps to the Langlands group of the global field. So you can just restrict a parameter along this map. With the formal definition of parameters, this is actually very non-trivial, because there you model a parameter by cuspidal automorphic representations of GLN. You can take a local component and take its Langlands parameter, but then who is there to tell you that the Langlands parameter, which is now valid in GLN, will have anything to do with G? Well, it turns out that it does, but that's a deep theorem that's embedded into Arthur's proof. Be that as it may, this map is there. And using this map, we now can state that this psi part of L2 is the direct sum over all pi's, which are irreducible representations of the Adeli group, with the property that the local component at each place is a member of the local packet. Oh, whoops, stumbling over this cable. So let me say that psi here is sent to psi v. So we can localize psi and look at the local packet that's given to us by 0.2. And then such a pi occurs with multiplicity, which could very well be 0. The multiplicity is m, psi, and pi. And the multiplicity was already discussed by Witek in his talk. So what is this multiplicity? Well, it is equal to the multiplicity of this mysterious sign character epsilon psi. So epsilon psi was a character defined by Arthur on the group S psi, with values in plus minus 1. And we're going to take the multiplicity of this sign character in the tensor product of all of these rho pi v's, tensor product over the places v. Each rho pi v is an irreducible representation of the local centralizer, but the local centralizer, there is a map from the global centralizer to the local centralizer via which we can pull back this representation. Almost all of these are trivial, so the tensor product is actually a nice finite dimensional representation. In the cases we're considering, it's even a character, so the whole tensor product is a character. And we're asking, is this character equal to epsilon psi or not? So the multiplicity is 0 or 1 for these special groups that we're looking at. In general, it could be bigger than that. So this is the statement of Arthur's theorem. And I want to say a few words about how is Arthur's theorem proved. Let's see, maybe I can do a little bit here. Shout if you cannot see here. So what is the method of proof? The method of proof, the essential tool is the Arthur-Selberg trace formula and the theory of endoscopy. So I'm going to do a little cartoon of the trace formula. It has a spectral and a geometric side. On the spectral side, we're going to sum over discrete automorphic representations and take their traces. But there are also additional terms in the trace formula that come from proper Levy subgroups. And by the trace formula, this is equal to a distribution of a geometric nature, where we're summing over regular elliptic elements up to conjugacy. And then there is a volume of the centralizer. More precisely, it's the Tamagawa number of the centralizer, but let me write volume suggestively, multiplied by the orbital integral. And again, there are proper Levy terms. So this is the trace formula. It's a cartoon of the trace formula, but I want to stick with a cartoon. Now, in order to use the trace formula for the proof of such a theorem, one needs to be able to compare it to a trace formula of a different group. And I'll say what other groups are going to be involved. But in this comparison, one has to stabilize it in order to be compared properly. So there is a stable version that looks like this. Here, we're going to be summing over the discrete parameters. And the trace of the automorphic representation is going to be replaced by a stable distribution, which will be the stable trace of the corresponding Arthur packet. Again, they are going to be proper Levy terms. And then this is going to be equal to a geometric side, where we're now summing over, if you will, the same kinds of elements, but up to stable conjugacy. And we have stable orbital integrals here, plus proper Levy terms. And the trace formula and the stable trace formula in this argument are going to be compared to each other. How are they going to be compared to each other? They're compared by the stabilization identity. So the stabilization identity is a theorem there is no volume factor here. So in the process of stabilizing, this volume factor, which is a Tamagawa number of G gamma, becomes converted with some endoscopic entities to the Tamagawa number of G itself. So it's independent of gamma and it pops out. There is no more volume factor here. So this is a theorem of Arthur for the non-twisted trace formula and a theorem of Moglin and Waltz-Bourget for the twisted trace formula. And it says the following, that the trace formula for G evaluated at some F is equal to a sum over the elliptic endoscopic groups of G with some explicit scalars times the stable trace formula for G prime at a function F prime, which is the transfer of F. And so now you're looking at this, and this gives you an identity, but really it's not just one identity, it's infinitely many identities because you have infinitely many functions F. But also you're not applying it in one situation, you're applying it in many situations, which fall under the following two basic categories. One is when G is the group GLN, but twisted by an automorphism. And then the G primes that occur are classical groups. And also products of such. And so in particular, if you're proving this theorem there, the G, the classical group you're interested in, is going to show up on the G prime side. And the G here in this theorem is going to be played by GLN. So that's one case of application. And the other case is where G is a classical group. And the G primes are products of classical groups. And so the idea is to have that this would give you a system of equations with enough interdependencies so that you, after a lot of work, you can resolve the system of equations and obtain the spectral information from here that you're going for. Now, in this comparison, one needs to, so see you have the trace formula here and then stable versions of it here. So let me put now primes. And let's think of this being on the left and this being on the right. In this identity, how does this comparison work? Where there are four major pillars of the comparison. One goes here and is called ECR, endoscopic character relations. One goes here, the proper Levy part of ECR, which is LIR, the local intertwining relation. One goes here and is geometric transfer of functions, which basically is in some sense the defining property of this map. And one goes here and is weighted geometric transfer. Again, this really is a cartoon in many ways, because first of all, the actual trace formula in its invariant form is not a neat identity between purely spectral and purely geometric distributions. In the process of making the trace formula invariant, you have to mix spectral and geometric distributions, so it becomes a little fuzzy. And moreover, and the same thing down there, and furthermore, there is cross-contamination going here because something that's dominant, say discrete here, or something that is discrete here may stop being discrete there. So there is cross-pollination, but let me not go into such details. Basically, this is roughly what it is, and I want to take a few minutes to explain what at least three of those things mean. So first of all, geometric transfer, what does that mean? Well, it means that the stable orbital integral at gamma prime of f prime is a linear combination of the orbital integrals of f at gamma, where gamma runs over conjugacy classes in G, which are related in the same geometric packet determined by gamma prime, the element here. And this is the transfer factor, which I'm just going to leave as a black box. And endoscopic character relations looks entirely analogous. It says that the stable character of psi prime is a sum over irreducible representations of G of f, which are somehow related to psi prime, which means they're in the same Arthur packet of determined by psi. And there is a spectral transfer factor. And then we have the character of pi at f. So it looks almost completely analogous. I want to open this box a little bit and tell you what this is, because we have enough by now enough notation to do this. This spectral transfer factor is very explicit. It is written in Arthur's work as a pairing between an element of the Arthur packet and an element of the centralizer of the corresponding parameter. And this, by definition, is simply the trace of rho pi. Rho pi is still up here, I hope. This is the irreducible representation of S psi associated to the member of the Arthur packet, evaluated at S times S psi. Now this S corresponds to the endoscopic datum G prime. So G prime comes along with an S. And this S prime is this mysterious element, which is given by the value of psi at the central -1 in Arthur's SL2. And here maybe this connects to David's question. If you only had a line, you wouldn't know how to form this, because this is really an element in the center of SL2 that you're sending over there. And that element plays a crucial role in the character identities, including stability. So from that point of view, I think the formulation with SL2 is more adapted to questions of harmonic analysis and automorphic forms, even if it may be less adapted to some other questions. This I don't know. Now, I find this S psi to be highly mysterious, kind of like this epsilon psi, although one could argue the epsilon psi is maybe even more mysterious. And if you're considering just tempered parameters, so parameter, I didn't say what tempered means. Tempered means it's trivial on Arthur's SL2. If you consider those, then both S psi and epsilon psi are trivial. But otherwise, they're very subtle. And so I was really baffled by this. And I once asked Jim, so I was like, how did you possibly think of this S psi and epsilon psi? I mean, they're so mysterious. And even the definition of epsilon psi, I mean, the definition of S psi is, okay, not so bad, but the definition of epsilon psi itself is complicated. And Jim thought about it for a while, and he said, well, if you look at what you have in front of you, it just becomes clear what you need to do. Or it never became clear to me. So I don't know, maybe I have to look at it more, or from a different, I tried changing the chair on various sides of the table. But anyway, this is the statement, and you can see this beautiful parallel between the two statements. In fact, we can make this even more parallel here. Instead of taking all the summands of L2 disk, you can take admissible representations that happen to occur here. And if you sum over those, you would add an m pi in front. And then the m pi is the analog of the volume. And then the trace pi is the analog of the orbital integral. So it's really a beautiful analogy. All right, but now I don't want to say much about weighted geometric transfer because I won't focus on it and it takes some while to write down. But I do want to say something about the local intertwining relation because this is, after all, the namesake of the talk. So the local intertwining relation happens where the parameter comes from a Levy subgroup. And of course, the interesting case is when it's a proper Levy, otherwise it collapses back to the endoscopic character relation. Now, in that case, we can assume by induction that the Arthur packet on M has been defined, and we can parabolically induce it to G. And this will decompose. I mean, this is unitary. Parabolic induction is unitary, semi-simple. This decomposes into some pieces. And we want to, the purpose of the local intertwining relation is to understand these pieces and to relate them to endoscope. So how is this done? This is done by the action of intertwining operators that are indexed by elements in the relative Weil group, which happen to stabilize the parameter psi. So how is this intertwining operator defined? It's defined as a product of a normalizing factor and an unnormalized intertwining operator. This is a scalar factor, and this is an operator. So how is this operator defined? This operator is going to act on the parabolic induction. And the parabolic induction is comprised of functions. And the operator is just given by an integral. In some sense, the idea is very naive. You want to push this function by a Weil element. When you push it by a Weil element, it stops being invariant under the unipotent radical. So you just brutally make it invariant under the unipotent radical, and that's the end of it. So we're going to integrate over the unipotent radical the function that we ended up pushing by the Weil element. Now that's too brutal, because part of this, the function is invariant under maybe some part of this. So let's kill the part of this that the function is already invariant under, and then that's it. That doesn't quite have the right equivariance property. So what we need to do is we need to extend the representation pi from the levy to a disconnected version of the levy that contains the Weil element and evaluate the representation there. And now this is modulo million questions of normalizations that I'm sweeping out of the rug. I mean, choices, I should say. This is the definition. Whereas this here is an arithmetic normalizing factor, which has one part known as the Shahidi constant. And the other part, so the other part is what I want to focus on. This is a version of a gamma factor, so something truly number theoretic. What is this gamma factor? Let me define it at any complex number. It's a product of an L and epsilon factors related to the Langens parameter for the Arthur parameter and an action of the L group of M on the dual of this space that we're integrating over. Whoop. Okay, so this is what this is. And the local intertwining relation is going to tell us something about how this operator acts on the parabolic induction. Namely, the local intertwining relation is the following statement. Take the trace of the action of a test function on the parabolic induction of the Arthur packet on M. But before you take the trace of this action, compose this action by the intertwining operator. This has to be equal to an endoscopic counterpart, which is exactly the same as the one for the endoscopic character relation. So if you like, it's a more refined version of the endoscopic character relation that accommodates the fact that you have a packet for M, but you may not know what the packet for G is yet. So you're trying to construct it by parabolic induction, and this involves understanding this decomposition using intertwining operators. So there is a general normalization of everything using Whittaker data. And Whittaker data usually specified by fixing a pinning and an additive character of the base field. I'm not putting this in the notation to try to keep it light, but yes. All right. So now, having stated this, one needs all four of these in order to be able to effectively compare trace formulas and extract the theorem from it. On the other hand, this same argument is able to produce versions of these statements from knowing weaker versions of these statements. So the game is now to try and cut down the input that we need to a manageable size, which can be supplied externally so that the machine can start churning and first of all, amplify that input and produce more of these. And then again, use them in order to produce the theorem that we're discussing. So the question is, what is kind of the minimal amount that we need here? Well, first of all, let me give you an example just by a reference of the machine producing stronger results from weaker results. And that's a famous result of Waltz-Projet, who shows that the fundamental lemma, which is a very special case of geometric transfer where everything is unramified, the groups, the test functions, implies the general geometric transfer. So a very weak version of this implies the full strength, and that was done exactly by such an argument. You look at the trace formula in stabilization. You start with the local question, you globalize it to a global question, you use the places judiciously and smartly, and then you get this result. So what we would like to know is certain weak versions of this implying stronger versions of this. Now, if you're thinking about tempered parameters, what can you do? Well, then results of Langlands and Shellstat give the endoscopic character identities and not full LIR, but enough information about it for all Archimedean places when psi is tempered. And so this is enough if you're interested in the tempered side of the tempered part of this or generic part of this theorem. This information is enough because at real places you have full power, and then you still need a little bit something more, which I'll call A27 for now. You need to know something about, yeah, let me say later what this is, but this more or less gives you everything. But when you're dealing with non-tempered parameters, then the real places are as mysterious as the p-adic places, and you really kind of lose control and you don't have enough. And so this is where some hypotheses needed to be made in order to proceed further. And these hypotheses were stated in Arthur's work as follows. There is hypothesis A27, which says that LIR holds for psi tempered or generic and generic representations, which means that if you look at the generic representation, there you have your intertwining operator. And really what it boils down to is knowing that the normalized intertwining operator acts by the scalar 1. And this comes very close to work of Shahidi. It's basically a reformulation of results of Shahidi, but there needed to be some connection between the language Shahidi was using and the language that was used in Arthur's book. Then there was hypothesis A26, which said LIR holds for all psi of twisted GLN. And then there was hypothesis A25, which said that both ECR and LIR hold for co-tempered parameters, which I'll define in a moment, of classical groups. And with this limited information about ECR and LIR, once you plug that into this global machine, it churned out full LIR and ECR everywhere. And in addition, it completed the proof of this theorem. All of these are local. The last thing is purely p-adic because co-tempered things only exist in the p-adic case. Exactly. So let me now explain what this means, and I'll focus on A25 for the remainder of the discussion. Okay, so now I'll discuss our results. So our theorem states that these three hypotheses hold. And with this, there is still one hypothesis left in Arthur's theorem, namely weighted geometric transfer, which comes down to the weighted fundamental lemma. This still is an input that has not been resolved, although rumors are it will be resolved very soon. But as of now, this is the last remaining input in that theorem. So I'll focus on A25, which is by far the hardest of the three. And let me first state what, let me see, how much time I have?
12:05, that would be kind of the plan.
20 minutes. Okay. You mean 11:35, or I was doing some arithmetic in my head that was failing. Okay, 20 minutes. So that should be good. So now, from now on, I'm going to say that F is local and non-Archimedean. And let me say a little bit about Aubert duality, which plays a key role in both the statement and the proof of A25. So Aubert duality is a duality on the whole category of representations of G, but let me state it for irreducible representations. And it can be expressed in the Grothendieck group as follows. It is given by a certain plus minus sign times an alternating sum of induction restrictions. So what you're doing is you're taking Jacquet modulo of pi and then parabolic induction of that back to G, putting a sign in front, and then summing over all standard parabolics. This turns out to be in the Grothendieck group an irreducible representation up to a sign, and we record this sign and call it beta pi. On parameters, there is also a duality one can do. And the duality comes from the symmetry that we have on Arthur SO2 and a Deligne SO2, and we can swap them. So psi hat of ABC is psi of ACB. And now we can define what a co-tempered parameter is. Psi is co-tempered if psi hat is tempered. Now, the point of Aubert duality is that it doesn't preserve tempered representations. And initially, you might think that this is a bug, but it turns out it's a fantastic feature because we want to use it to import information from the tempered case into the non-tempered case. So the role that for tempered representations was played by the Langens and Schellstadt results that were derived by local means is now going to be played at finite places rather than infinite places and co-tempered parameters. Those are going to be the control parameters that are going to make the global machine work. And so our theorem in this setting, which amounts to A25, says the following, that let psi be co-tempered. There exists a packet constructed by hand, and I'll tell you, it's actually, once you know what to do, it's very easy to do, and a map to the irreducible representations of S psi, such that, number one, ECR holds, and number two, if the parameter happens to come from a levy, then LIR also holds, which is exactly the input that we need to run the machine over there. So in the remaining few minutes, I want to just give a very, very brief indication of how one may attempt to prove these results. So proof of ECR. All right. So there is something very easy and very obvious that you can try to do. And if it's easy and obvious, why not try and do it? So attempt 1 is the following. Well, we already have the packet of the dual of psi, because by definition, the dual of psi is tempered, and we're assuming that we have covered the tempered theory already. This we could do because there, the crucial inputs were given to us by Langens and Shellstad. So we run the machine, the tempered theory is done, and now we have the tempered packet. Well, why not define the packet here just by using Aubert duality? So take this packet to be the Aubert duals of that packet. Great. Well, from the tempered theory, you already have a map like this, satisfying ECR. And on the other hand, if you look at how the dual parameter is defined, you'll notice its image doesn't change. And so anything centralizing the one centralizes the other and vice versa. So the centralizer groups are identical, they're equal, they're the same group. So you have an identity here. So why not just do this? Well, it's because ECR doesn't work. So something more mysterious is happening than just doing this simple thing. Okay, so let's go attempt 2. Attempt 2 is the following lemma. Assume pi psi is given and satisfies ECR. Let's pretend that the thing that we want to do has already been done by some kind of benevolent being. Then what can we say? Well, then, first of all, this packet is indeed given by the Aubert duals of the dual packet. Great, so that much in the above picture was already okay. We were not completely terribly off the mark. I'm assuming something that I don't have, which is the thing I want to be true is true. I have a packet, somebody gave it to me, I don't know what's inside, but I do know it satisfies ECR. No, I'm pretending I know, and I'm trying to extract, if that were true, what would have to be true? What would ECR have imply? And then I'll turn things around and say, oh, let me see if what I just found out.
I just don't understand. I understand you're assuming that you have a pi psi that satisfies the endoscopic character.
Exactly.
And you wrote a second statement with 1.
Okay.
And
See.
Are you deducing that from the assumed character?
Yeah, I can explain. So when I was working on the book on Burhat-Itz theory, the copy editor killed all the thens in all the theorems and said, this is bad English. You state your assumption and then you say 1, 2, 3, you say what holds. And so now I was feeling reticent to put the then, even though there was some urge. So maybe I should say then the following is true. And if this makes you more happy, you should definitely take it up with the copy editor and explain to her that the then is useful. So yes, this assumption has the following logical implications. First of all,
I mean, that's what I understood you right.
Yeah.
My question was, is it supposed to be clear to us that that's true?
No. So this is a lemma, and it has some proof, and the proof takes some work. So it's not evident immediately, but it's a logical implication. It takes a few pages, and I mean it's not so easy. But that it is true. First of all, this. Second of all, the pairing between S and pi, which remember this means I take this map that I'm trying to construct, but now I'm assuming it's been given to me, and I take the irreducible representation corresponding to pi, and I take the trace of that at S. What does this have to be? Well, this has to be equal to the same thing for the tempered side, but modified by certain signs, which I was planning on discussing, but I don't think I have the time to discuss. So at least not on the board. I'll say verbally what I mean by this. This beta phi is analogous to the beta pi here. Namely, phi gives you a parameter for your group G, which you can continue to GLN. It gives you a parameter for GLN. It gives you a representation of GLN. So you can do Aubert duality for GLN. That's not what beta phi is. There is also an Aubert duality for disconnected GLN. And the beta phi measures is the analog of this sign, but for the disconnected group GLN, and for the representation of GLN corresponding to this phi. And then we can also decompose phi into a product of phi plus and phi minus, depending on the element S from the endoscopic character relation we're trying to show, and then do the betas here separately. Okay. So in other words, we can measure the failure of this diagram to commute if ECR is to hold. And the third part of the statement is that we can also say what this pairing does to this mysterious element S psi. Namely, this is just the product of the signs beta pi and beta phi. Okay, so the proof of this involves crucially a result of Hiraga on the compatibility between endoscopic transfer and Aubert duality, and also work of Mogla and Bin-Shu on cuspidal support of representations expressed in terms of enhanced Langlands parameters. And it was also independently obtained by Baing Liu, Chi-Heng Lo, and Freydun Shahidi. But what you can now do is you can turn the tables around, and now instead you're going to take 1 plus 2 as a definition. So 1 is a definition of the packet, and 2 is a definition of the pairing. And then you can check 3 and ECR. Okay, so this is the end of the proof, well, the end of the sketch of the proof of 1. And so now we can go to LIR, which is really the meat of the result, or the tofu of the result. So I'll try to just very cartoonishly give you an outline of what one does there. So proof of LIR. So now we are in a situation where we're considering a parameter coming from a proper levy. And remember, you either remember or look at it. The question is it still there? I erased it. So what was LIR? LIR was the trace of the intertwining operator composed with the function acting on parabolic induction of the packet. LIR said that this is supposed to be equal to its endoscopic counterpart. This is what we're trying to prove. But on the other hand, we already have some information because we proved ECR. And ECR said that this is supposed to be the sum over the packet times this. And so we can now dispense with this thing, not go to the endoscopic group, and just stay on our group and say we're trying to prove that this on our group is equal to this on the same group. And so that means that LIR is equivalent to the following statement. If you take the intertwining operator and restrict it to a particular constituent of this parabolic induction, it has to act by a scalar, and the scalar has to be exactly this scalar. Okay. Now, this is still completely mysterious because you're saying an intertwining operator that involves an integral and some gamma factors and a whole lot of other things is you're supposed to be able to say exactly by what scalar it acts on any representation, and it has to be this kind of endoscopic quantity. Okay, So the first basic proposition that you can prove is the following, that the intertwining operator and Aubert duality commute up to scalar. Which means, so Aubert duality, I gave it in the Grothendieck group, but you can define it as a functor on the category of representations. Being a functor, you can apply it to any endomorphism, and it's going to give you another endomorphism, and you can check that this endomorphism that you get is again an intertwining operator, but normalized in some way that you don't know. So it's off by, which could be 1, but you don't know, from what you want. And so this now immediately gives you 2 possible approaches to what you're trying to prove.
Everything is unitary at this point, right?
Yes, because we know by induction that the Arthur packet on M consists of unitary representations. All right, so we have attempt 1. Compute the scalar. And once you compute the scalar, you infer LIR for psi from LIR for its dual, which is tempered, where you know LIR to hold already. Okay, so we tried this for many months. And in the end, we concluded it's too hard for us. We just can't do it. This scalar by which the 2 intertwining operators on the tempered and co-tempered side differ by under Aubert duality, it's just a nightmare. We tried to do Heck algebra calculations and all kinds. It was a disaster. So we said, okay, we gave up. We cannot do it. So attempt 2. Don't compute the scalar. Okay, so that worked out really well. But then we still had to do something. Okay, so what did we then do? We started with a big Devisage argument, which had the following steps. First of all, we can reduce to M in G maximal proper. That's not too hard. That uses the fact that intertwining operators are multiplicative and respect in induction. So that's OK. And also, well, so if M is maximal, what does it look like? It looks like a general linear factor and some classical factor of smaller dimension. Well, if that's the case, then the representation that we have on it is going to have some G linear part and some classical part. And we assume that the Arthur parameter of this linear part is irreducible. And that can also be done. OK, so that's the first part. Now, what is the second part? The second part is that we are going to know that the parabolic induction of such a sigma has at most 2 bits. Why is that? Because the same is true when you take duality. Then you're reducing something tempered from a maximal parabolic. It has 2 parts. And by functoriality of Aubert duality, you know this is true here. Now, using the proposition here, you know that LIR is going to hold up to a global scalar. So it's enough to pin it down on one of the possibly 2 representations. So proof for 1 pi in parabolic induction. Well, which one? You have some kind of non-tempered thing. How are you going to possibly say which one you're doing? Well, here comes an idea from work of Tadic. We introduce something that's called a highly non-tempered summand. The definition is too technical to say in a talk, and I'm already more or less running out of time. But the basic idea of a highly non-tempered summand is that you can compute its standard module explicitly in terms of the standard module of the inducing representation sigma, which is generally not at all the case. But for these, you can do it. And as a result, you can express the Langlands quotient from the standard to that summand as explicitly as a normalized intertwining operator. And when you do this and use multiplicativity of normalized intertwining operators, you end up from the operator identity you're trying to prove to a scalar identity of the following form. It involves a quotient of gamma factors, but for different parameters. On top, we have the Arthur parameter of the inducing representation. And on the bottom, we have the Langlands parameter of the inducing representation. And this at 0 should better be this endoscopic quantity. So we reduce LIR to such a number theoretic statement. Great, except this is also hopeless, even though it's just a scalar statement. So what do? We cannot prove it directly. Instead, we do a second devisage, which uses the theory of derivatives that has been used actively by Mingus and Atobe and other people for the unitary dual problem. And we use that theory to devisage down to a situation where the inducing representation is a very special shape. It's almost supercuspidal. Means it's maybe not quite supercuspidal, but if you find a supercuspidal representation in any of its Jacquet modules, then that supercuspidal has to be unitary. And so after this devisage, you end up at that case, and there you actually can compute it. It only takes about 10 pages then, but then you can just by hand, using the Zelevinsky-Moglan classification, you can actually compute both sides and observe that they're equal. And so that's then the end of the argument. So I'll stop here.